All right. So we're continuing today with our ongoing discussion with sealed with radioactive materials, chapter 16. And so the next thing that we're going to get into then are sealed radiation sources. So what this really is all about is when it comes to certain types of applications of radioactive materials. The manufacturer of those radioactive materials will put high levels of the isotope inside of a steel tube. And then that gets put into some sort of medical device. Now, there's a couple of applications for this. The most common of those applications is for the irradiation of goods. Now, why would we want to take certain types of materials and expose them to radioactive decay? And the primary reason is either for medical treatment. So we're using them to do radiation therapy for things like cancer or other kinds of disease controls. We're using it for the sterilization of foods or the preservation of foods, or sometimes there are other purposes as well. But these are certainly the primary ones. We also know that things like gamma rays are used in the plastics and rubber industry. We can irradiate the polyethylene that makes the plastic or the rubber that goes into tires. And the reason we do this is because the radiation will stop the growth of insect populations, of micropathogens, mold, bacteria. It will help preserve, lengthen the shelf life of meat, chicken, turkey, produce, poultry, vegetables, fruits, those kinds of things. Irradiation has the potential to eliminate bacteria from those surfaces as well. Now, the question you might have on your minds is, well, that sounds like a really good thing to, preserve shelf life and to, kill things like E. coli but we just went over all this stuff about how radiation can make us really sick, or can have really nasty effects on our body. What if I don't want that? Well, the good news there is that if something has been treated with radiation as some sort of sterilization measure, it's going to have on it the Redura symbol. The Redura symbol is this symbol here. And that symbol tells us that we have some sort of radiation source that has been used on this item, whether it's a food item or some other sort of material. So no, you will not be exposed to irradiated ground beef without your knowledge. In fact, most manufacturers don't do that. I mean, if you go to a grocery store, most of the stuff there is cut and produced on site. Chances are pretty good they're not going to do irradiation there in the back of the JC. But it does have other applications. So again, this is more on the preserved end of things. This symbol here, the ISO symbol, is something that is put on sealed radioactive sources. So if we're looking at what the object is that is used to irradiate the food, irradiate the materials, you'll see the ISO symbol on there. And I think it's pretty self-explanatory what it's saying. We've got our radioactive symbol here on the top. We've got these lines coming from the radioactive symbol that are basically telling us to get out of there or we'll die. Now, how we go about detecting radioactivity? Well, the answer to that question is it depends. There are lots of different instruments out there that have the purpose of detecting radioactivity and measuring the radiation in the world around us. Those can be very, very personal machines, like badges. They can be more general machines, like Geiger counters. But when we're trying to get an idea of how much radiation a person has been exposed to, or how much radiation is in a particular area, we have to use personal monitoring equipment to do that. And that personal monitoring equipment comes in a variety of forms. Now, the most common of these forms is something called the Geiger counter. Geiger counter is, well, basically looks like a calculator, has a screen on it. You'll actually use a Geiger counter in the radioactivity lab, which is, I think, the next lab that you're going to do, not today's. Geiger counter looks a lot like this. So again, it's about the size of the calculator. It's palm held. It gives you readings of the total number of counts, the millirems per hour, the counts per minute, and all those have different uses there. So this is probably the most common one. This one has the ability, turn it on to the audio line there, it'll actually make a clicking sound every time it encounters a radioactive particle. And what you really get out of that is, doesn't matter where you take it, it'll always click somewhere. There are radioactive particles around us all the time. Most of the time, it's just too few for us to notice or even care. But if the situation is different, obviously, it's maybe a different kind of thing as well. In workplaces where there are radioactive materials being used, things like doctor's offices, hospitals, these badge dosimeters are kind of the most common. What they will do is they will actually light up when you start to get into a dangerous range of radiation. That's why they're called luminescent dosimeters. So the person wears them on their person as maybe part of a badge, and they measure your total exposure. And if it gets too high, they light up, and that gives you a warning to get yourself out. These are called pocket dosimeters or pen dosimeters. They're intended to clip on to like the pocket of a shirt. And they kind of do the same thing. They don't light up, but they do give some kind of a warning if the amount of radiation comes too high. So when it comes to measurement of radiation, there are a couple of terms that we're going to end up using. One of those terms is activity. Activity is a description of the intensity of a radiation source. Now, activity in general talks about total activity. So what is the total intensity for all the radiation sources that might be present in a given area? To get to something called specific activity, what we have to look at is we're looking at a particular radioisotope and we're measuring how much radioactivity it gives us per unit mass of that isotope. So activity is our primary way of measuring radiation. And there are a number of different units that come along with that. Now, the units of activity, all of these can be measured with one of those radiation detectors, whether it's a dosimeter or a Geiger counter like what we showed you first. A radiation detector can be used for that purpose. And what we can get out of that radiation detector are things like number of radioactive particles, number of disintegrations in every second, or one more common way of doing it is using units called curies or becquerels. And those are specific units of disintegrations. So here are the becquerel and the curie. The curie is a representation of a radiation equal to 3.7 times 10 to the 10th. That's 37 billion disintegrations per second. Becquerels are kind of the classic, the scientific community accepted version. They are equal to a single disintegration per second. As you might expect, for a radioactive source, this is a really small unit. So we usually see one of those metric prefixes attached to it. So mega would indicate million becquerels. Giga would indicate billion. And tera would indicate a trillion. So generally speaking, we are talking about large, significant amounts of radiation if we use becquerels. So the curie is a bit older of a unit. And so we don't necessarily see it used as often because it's not the kind of standard unit. But as I said, standard unit becquerels, really, really small. So usually we see a prefix attached to those relatively often. Some other units of radiation, we have the Renkin, which is capital R. Now, you can see from the description of a Renkin is very very specific. This is the amount of radiation that generates 2.1 billion units of charge in a milliliter of dry air at standard atmospheric pressure. As you might imagine, with something that specific, it's not used very often anymore. It is an obsolete unit. Renkins are not usually used terribly often. A more common usage is the rad. The rad is a radiation absorbed dose. This is the amount of radiation that has been absorbed per gram of body tissue. And so what we can see is that for all practical purposes, one Renkin has been deemed to be equivalent to one rad. So instead of using the Renkin, we tend to use the rad instead, the radiation absorbed dose. And why we use the radiation absorbed dose is because it's easier to measure. It's easier to measure the amount of radiation that's been absorbed by a body system divided by the mass of the body system. And it so happens that it happens to be equal to that Renkin value anyway. So it's an easier way of doing it. So again, we're not going to see Renkins, not very often. Rads we're going to see quite more frequently. Now, closely related to the Renkin and to the rad is something called a REM. REM is called the Renkin Equivalent Man. And it's just another way of kind of looking at things. So here we're talking about kind of flipping it around. Instead of looking at the total amount of radiation per gram of body tissue or per kilogram of body tissue, we're looking at how much body tissue is damaged by a single dose of X-rays or gamma rays. So it's kind of flipping the idea around a little bit. Another common unit is the gray, which is abbreviated GY. It is another dose radiation. It's equal to the absorption of 1 joule of energy in every kilogram of tissue. Bringing it back to the rad, the radiation absorbed dose, there are 100 rads in every gray. So really, the most important thing that we can kind of draw out of this is we can notice that everything comes back to the rad. All of our units that we've talked about have had some kind of tie into the rad as a unit. And so when we look at radiation kinds of measurements, rads are going to be the most common radiation unit that we find. Now, that doesn't mean that we won't see REMs, or we won't see grays, or we won't see becquerels. But rads are going to be more common than most. The last unit here is called the sievert, SV. Now, the sievert is a unit that's a little bit more newish. It's one that is also tied to what we call the Common International Unit. So sieverts are found, and one sievert does equivalent to 100 Renkin Equivalent Men. So from that standpoint, this is the most preferred unit for measuring exposure. Now, that's not to say that it's not the most common one. Again, Rads and Renkins have been around for considerably longer. But the sievert is the one that kind of crosses international borders. So we do see it used quite often there. Putting it into context, again, one sievert is equal to 100 rem. And finally, remember the SI unit is our common international unit. So just like we saw becquerels as being the common international unit for just strict measurement of radiation count, the sievert is going to be the dose equivalent of that. So we've talked about radiation. We've talked about just some general things in terms of the different types of radiation and what it can do to your body. We've talked about measurement of dose of radiation. Let's get into what happens when we are exposed to radiation. What are some of the ill effects that come from that? Now, the one thing that you should know is that, I've said this before, we're going to say it again. You are constantly being exposed to radiation. There are radioactive particles in this room right now, most of them coming in the form of radon. Most of the radiation that we encounter is just naturally occurring radiation. It's a part of living on planet Earth. Has no other source other than just natural geology at play. But when you do get exposed to other forms of radiation, the non-natural ones, the ones that are not just in the background that we encounter every day, like what you might get at a hospital or at a doctor's office, at the dentist, from working in certain kinds of industries. Those do raise your overall risk for getting some of the ill effects, but if they're kept in relatively small quantities, we generally don't worry too much about them. If you are exposed to a large amount of radiation, however, that's when we can get into some of these other kinds of effects. Things like radiation sickness, which is kind of a blanket term for just a large collection of health issues that you can get as a result of being exposed to radiation for a period of time. And that period of time does not have to be a long period of time. You can get radiation sickness based on just short-term exposure, if it's the right isotope and if it's the right dose in that short amount of time. Other effects are a little bit more chronic or latent, where we're getting effect of long-term exposure, and that long-term exposure to radiation is gradually wearing on your body system and eventually develops into something else. What happens to you depends on 4 factors. Type of radiation that's absorbed, the energy of that radiation, what specific isotopes are being used, and your overall age. Those four factors play into a very specific kind of idea. So we're going to take some time here to talk about those four factors and how specifically they would make a difference on the effect of radiation on your body. So let's start with this chart. This is a chart of background radiation that you are exposed to on a relatively daily basis. And if you look at it, the majority of what we are exposed to on a daily basis are radon and thoron. Radon and thoron are naturally occurring substances that are just around, and they undergo alpha decays. And the results of those alpha decays are other radioactive substances and alpha particles. Now, luckily, we know that alpha particles pose minimal damage to us because our skin, our clothing provide most of the protection we need against those. So while they are background radiation, not much to them. The other forms, naturally in your body, I talked about this, the idea that in the act of eating, drinking, breathing, and living, you are constantly exchanging carbon, you're constantly exchanging different elements. Some of those elements are going to be radioactive, but they're in such small quantities, again, doesn't really make a difference to us. The other things, the other primary areas, the medical field, just in general, X-ray machines, other kind of radiological treatment, they produce small amounts of background radiation that we would encounter. Cosmic radiation, some radiation is able to seep through our atmosphere and come down here. A relatively small amount though. Gammas from rocks and other geological footprints. Again, naturally occurring. We're talking about a relatively small percentage of the pie here. And while those gammas could be potentially damaging, chances are also pretty good that we're not exposed to too many of them. So unless you happen to live in a pocket of the world that has a uranium or a radium deposit in it, chances are pretty good that any gamma radiation that you encounter is just slight. What are some of the signs and symptoms that you can see based on dosage? So if we were exposed to a dosage of less than 3/4 of a gray, we probably wouldn't see much effect on our body. At most, the most sensitive humans on the planet might be induced to vomiting or retching at that dosage, but generally speaking, not a whole lot happens to it. Up to 1.5 grays, we will see nausea and vomiting, fever, infection, anorexia, all possible symptoms. Up to 3 grays, we can see fatigue and weakness and bleeding, fever and infection coming in. At this level, we also see that the first deaths are possible. So a death rate of less than 5% is possible with doses up to 3 grays. Up to 5.3 grays, now we're seeing more infection, we're seeing ulceration occurring. This is getting us up to a higher death rate, all the way up to 50% at this particular dosage. And then up to 11 grays, well, you're circling the drain here. At 11 grays, we have a death rate of 100%. People do not survive radiation of that level ever. Internally. Depending on the dosage. You, at 11 grays, it would be relatively fast. In the lower rates, it can be prolonged. It would just depend on, so, you know, for example, at the three gray mark, if you're one of the unlucky 5%, you know, the infection that would be caused by the radiation source coming in and bacteria kind of sleeping in, that could take a period of days or even weeks. But since your immune system really, in those particular people, your immune system just has been decreased to such a degree that you can't fight out of it, that's ultimately what causes the death there. But again, it's very low. And you have to understand, these are also, we're giving it higher doses of radiation. So that's when you get you start to get pockets of bleeding in your internal organs. So generally speaking, we know, and we've talked about this before, alpha radiation, despite being energetic, its overall size makes it very easy to be absorbed. So your epidermis, the outer layer of your skin, is usually enough to absorb alpha radiation and largely block it from your other tissue systems. Beta radiation, on the other hand, you know, goes deeper into your tissue. Gamma and X-rays are the most severe. And again, we've talked about all of this already when we kind of introduced the three types of radiation and their penetrating power. And we used a different kind of drawing there. The drawing we had then was all about you know, what it does to your skin, but now we can look at different materials as well. So here we have 4 different materials, and we can see that for the most part, alpha, beta can be stopped by certain thicknesses of plastic. We also talked about aluminum the other day. Beta cannot penetrate your hand fully. It stopped somewhere in your tissues as well. Gamma passes through everything. Depending upon the thickness of the lead, the gamma can also penetrate the lead as well if it's not thick enough. Usually we need several inches, if not a foot, of lead to get enough density, enough present there to fully block the passage of those gamma rays. So the reason why they put those lead vests on you when you go to take an X-ray to protect your internal organs isn't because the lead is going to completely block them out. That would require way too much lead. But what it's going to do instead is it's going to put enough of a barrier that's going to slow down some of those gamma rays and protect your organs better than what you'd be able to do by yourself. Another important thing to know about radiation is the inverse square law. What the inverse square law tells us is that there is a relationship, a inverse square relationship between the intensity that you see for a particular substance and your distance from that radioactive source. As your distance away doubles, the intensity of the radiation goes down by a quarter. So it's a square of the difference. So if I double the distance, the intensity goes down by 1/2 squared, 1/4. If I triple the distance, it goes over by 1/3 squared, 1/9. If I quadruple the distance, 1/4 squared, 1/16. So at every length and at every distance that I can put between myself and the radioactive source, I am lessening the intensity of that radiation and therefore the dosage that I'm going to be able to absorb by significant portions. So when it comes to radioactivity, obviously, if there is an active source of radiation present, you don't want to be right on top of it. The more distance that you can put between yourself and it, the less intensity, the less radiation that you'll end up absorbing. So let's talk about some specific isotopes. There are certain isotopes that are going to be more dangerous to you than others. And that's because they will have certain effects on the human body. They will have targeted organs that they go after. Not necessarily because that's what they're designed for, but that's more about what your body system does with that element. So for example, strontium and radium, which can be radioactive, can replace the calcium in your bones. Now, why can they do that? Well, look at where they are on the periodic table. Strontium and radium both are in the same group as calcium. So from an ionic standpoint, they mimic calcium. And so because of the way that your bone structure is set up, strontium and radium can go in there by accident, and they can start weakening your bones. They can give you bone cancer. They can give you leukemia as a result. Iodine. Iodine has a particular target in your thyroid gland. Why your thyroid gland? Because when you ingest iodine, iodine is actually used in your thyroid gland to help stimulate that thyroid gland. Helps the thyroid gland do what it does, keeps it perked up. That's why iodine's put in things like salt. Iodized salt is used for the particular purpose of providing your body with iodine, which helps lead to better improved thyroid function. So if you happen to encounter a radioactive isotope of iodine instead of the normal stable iodine, that iodine would be concentrated by your body and sent directly to your thyroid gland. And if enough of it gets there, it can lead to thyroid cancer because the iodine would start to decay and cause tissue damage inside of the thyroid gland. Now, what about age? More often than not, when we talk about age effects of things, we usually talk about things that are affecting the very old. Most health scares, most health crises focus on the elderly generation because their immune systems have been compromised from the fact that they've been living on this earth for such a long time. When it comes to radiation, however, that's not actually the case. The most vulnerable people that have dangers being exposed to radiation are the very young and the developing. People like unborn children, infants, young people, people who are still going through the processes of puberty and adolescence. They are at highest risk because their bodies are still developing. Remember, your whole body system is based on DNA. And as you grow, your DNA needs to divide and separate to create new cells, to create new tissues, to help develop organs, to help do lots of things that your body does to take you from a single-celled organism at conception to adulthood. Now, in your adult life, you're still generating and making new cells, but you're not making nearly as many. Whereas in a young child, where they might grow from being 18 inches long one year to 36 inches tall the next year, their bodies are going through a lot of cell division. Their DNA is being constantly exposed to their internal systems. If radiation gets into that system, it can hit that susceptible DNA, disrupt it, and that's where we can get cell mutations. That's where we can get nuclear mutations taking place. That's where we can get things like cancer and other nasty effects, leukemia, in children, because their bodies are more susceptible to those kinds of change. And just one little change in that DNA can cause a massive effect on the rest of what they do. So when it comes to radiation exposure, all of us are susceptible in some kind of way. But the young especially are susceptible because their bodies are definitely undergoing the most change in that time period. So we're going to end here today talking about workplace regulations. So at the very beginning of this chapter, we talked about the NRC, we talked about the Department of Energy, and all of the things that they were responsible for doing. Nuclear Regulatory Commission, Department of Energy, they do the research, they do the what to do with the storage, they deal with nuclear power plants, they do all that stuff. The stuff that isn't under those two organizations' purview, OSHA steps in. Occupational Safety Health Administration. And their regulation goes as follows. No employer can expose individuals to 1 calendar quarter a dose in excess of limits except in specified circumstances. And for minors, that quarter drops down to 10%. So there are limits on the amount of radiation that you're allowed to be exposed to in the workplace if you work in a place that has radioactive materials involved in it. And again, It comes down to age here. Why are there different limits on 18-year-olds and under? Their bodies are still developing. They're still in that kind of vulnerable class, although they are starting to grow out of it. The specified circumstances are very specific. And they're very, very tightly regulated as a result. If radioactive materials are present in the workplace, OSHA requires that your employer conspicuously post any applicable signs for that. And when I say conspicuously, I'm going to show you what the placards look like here in a second. These are placards that are hard to miss. They're not your standard, yellow and black or black and white kinds of placards. They stand out for a variety of reasons. They want to catch your eye and let you know that something dangerous is going on. So there are 5 different types of radioactive warning signs: the radioactive materials area, radiation area, high radiation area, airborne radioactivity area, very high radiation area. All of these signs are going to look the same. The difference between them is going to be the wording on those signs. And the wording, what the difference is between a radiation, a high radiation, or a very high radiation area, has everything to do with dosage. And so OSHA has limit ranges for what that actually entails. But like I said, the signs themselves usually stand out in some kind of way. Often magenta is used as one of the colors on a yellow background or on a blue background. This one in the middle is particularly unusual. Even this one on the end, which is more of your standard black and yellow, the black and yellow with the magenta lines in it does kind of help it to stand out differently. So that's where we're going to stop for today. When we come back from spring break, we're going to look at kind of more of the body effects, and then we're going to kind of close out and talk about nuclear power and some of the applications of radiological materials. So with that said, have a great break. I'll see you in, 10 days.